All right, now the next one is engine data, and this is mostly pretty straightforward depending on your knowledge of engines. So the first one, I need to go ahead and state that some of this changes depending on what type of engine the plane has. So the first one that you're going to see in every CFG file is general engine data. This defines the type of engine the aircraft has, the number and position of the engine, as well as a couple of scalars. So general engine data, engine type, it's going to be a number between 0 and 5. 0 is a piston engine, 1 is a jet engine, 2 is none, so that would be for glider, 3 is helo turbine, i.e. the EH-101. Now 4 is rocket, and 4 is actually not supported, so don't go putting rockets on things, because apparently they don't work. The CFG says it's just not supported. Maybe they planned on adding it in the future, I don't really know, but 4 is rocket, apparently. And lastly, 5 is turboprop, 5 being the type of engine this plane has. Cessna 208 has a turboprop engine. So you put 5 there. Now, the rest of this data changes depending on what type of engine you put in there. We'll get into it as we go. This next one is engine.0, and it can be 0, 1, 2, 3. That's it, actually. Because the ESP-based sims only support a maximum of 4 engines. So, by the way, Dovetail, Lockheed, there's something you can fix. There's something that needs improvement. Can we please have more than 4 engines? That's a very weird limit. Anyway, this is where you define the position of the engine as well as the type. Now, quick note. If we look at our 3D model again, there is a black speck right here where the prop is. You can kind of see it where all these lines come together. And there's 2 more right here. Now, these 2 up here are the fuel tanks. We'll get into them later. But this one here is where the engine is. So it's important you place this dot not exactly where the engine is, more along the lines of where do you want the thrust to be coming from, because that is where the thrust of the engine is going to come from, unless you define a propeller offset, which we'll talk about later. So fuel flow scalar, oh, by the way, these coordinates up here, they're in relative datum reference, longitudinal, lateral, vertical, just like before. Now, fuel flow scalar, this is just a simple scalar value for the fuel flow. Now, fuel flow itself is defined by stuff in the air file, but you can further define it via a scalar here. 1.0 is normal, less than 1.0 is less than normal, and more than 1.0 is more than normal. This is a good way of making the planes different. So you can have like the same air file for different models, but kind of tweak them a bit, because again, no 2 airplanes are ever the same, even ones of the same make and model. Now here we have the minimum throttle limit. This is the minimum % of throttle, and you want this to be negative if the engine has reverse thrust capability. So that would be jet engines with reverse thrust capability, or some turboprops that have them. You would make this negative. As you can see, it's minus 0.25. Now, the rest of this changes depending on the engine type. For jet engines, helo turbines, and turboprops, you will need turbine engine data, and then you will also have a separate section for turboprop, and for helicopters there's going to be helo engine data as well. For pistons, you just need piston engine data, which I have right here, and for turboprops and pistons, you also need to have propeller data as well. Now, I'm not going to go into all of them. Read the SDK documentation I'm going to link to in the description for details on everything that goes in here. But we'll try to go over most of it. I have put the engine types you don't need for this particular aircraft in here, so we can go over some of it. First one is piston engine. Now, this aircraft doesn't have a piston engine, so I'm not going to explain everything. I'm just going to sort of touch on it. So, power scalar, this is a scalar of engine output power. 1.0 is normal, as we talked about before. Cylinder displacement in cubic inches per cylinder. The compression ratio, the number of cylinders the engine has, the maximum rated RPM of the engine, the maximum rated horsepower of the engine, The fuel metering type, 0 can be a fuel-injected engine, 1 is a gravity carburetor, and 2 is an aerobatic carburetor. Now, these things actually do change the way the engine behaves, particularly with the gravity carburetor. If you pull negative G's with a gravity-fed carburetor, you can shut the engine off, and that is doable in FSX. That is one of the undocumented, sort of untoggleable but triggerable failures. Like pitot icing is another one, as well as prop strike or engine failure as a result of prop strike. There's a few failures that can happen as a result of pilot action that can't be toggled on and off in the failures menu. And one of them is engine failure due to negative G's with a gravity-fed carburetor. Cooling type, is it air-cooled or is it liquid-cooled? Normal starter torque. This is the torque that the starter motor kicks out. If you've ever had a problem with an engine, when you're starting an engine and it failing to start but knocking the plane around all over the place, this is where you should come to look at that, because it probably means they turned the starter torque up too high. Turbocharger, these next 3 here, actually these next 4 are for turbochargers. Does it have a turbocharger? 0 for false, 1 for true. Maximum design manifold pressure of the turbocharger, minimum design manifold pressure of the turbocharger, and the critical altitude, which is the altitude to which the turbocharger will provide maximum design manifold pressure. Above that altitude, it starts to decrease. So you can toggle on and off turbocharger here. Now, going a little bit further, we also have emergency boost types. We can define 0 for none, which is most engines. 1 is a water-injected boost. 2 is a methanol water injection blend boost. And 3 is war emergency power, which is commonly found on World War II fighter planes. Now, you also define the manifold pressure boost offset and the boost gain offset when defining the manifold pressure, or defining the emergency boost. So boost MP offset is the additional manifold pressure supplied by emergency boost. So like if the engine's running at 20 on manifold and then you activate the boost, how much is going to get added to that 20, basically. And this last one is the gain offset, multiplier on manifold pressure due to emergency boost. Now, quick thing here, do not use emergency boost to simulate things like nitro injection or supercharger. Starting with acceleration and on, superchargers and nitro injections are modeled separately now, so you don't have to use an emergency booster to model those. Fuel air auto mixture, this decides whether if fuel air auto mixture is available. Some airplanes do have an automatic mixture thing. Piper Cub, for example, is one of those. I think some modern planes have like a modern FADEC or something like that. It's not actually FADEC, but whatever FADEC is called for piston engines. Auto ignition is auto ignition available. Maximum rated mechanical efficiency scaler. These are all, these next 4, just scalars on things like max RPM, idle RPM, max RPM friction, and idle RPM friction. Best power specific fuel consumption, which is the specific fuel consumption at best power mixture. It's a ratio. Now, these last 4, you're not commonly going to find on add-on planes, and you're really only going to find them on one default plane, and that is detonation onset. Now, this was a feature added with FSX acceleration, and what it is a maximum manifold pressure where if you cross above that, detonation begins to occur. Now, what is detonation? Detonation is where the fuel-air mixture inside of the cylinder explodes instead of burning smoothly. And what happens, that can be caused by several things, but notably some engines running at too high a power can cause it, and that's the trigger in FSX, and this is where you decide where that trigger is. So let's say you have an engine designed for about 20 manifold pressure, and if you exceed 25, so you can put like 25 in here. If red line is at 20, which is a bit low, but let's say it is, red line's at 20, you can give them a safety margin, but if they go above 25, you start hearing detonation. Now with FSX, it actually has a sound effect for this. you will hear a rattling sound followed by several pops, and each pop is an explosion that is killing one of your cylinders. You will lose one cylinder with every pop, which happens on about 1.5 to 2 second intervals if you don't do anything about it. And once you lose a cylinder, that's it. That cylinder's failed. Once you lose all cylinders, you've lost your engine. With each cylinder, you lose power from the airplane. So that is where you define that, the detonation onset. Most add-on planes don't make use of this feature, which is sad. I really wish they would, because it's a way of sort of making sure the end user's flying the plane properly. Now, if you do define a detonation onset, you might want to define a anti-detonation system, especially for race airplanes. We'll talk about that later on in the video. The last one is the supercharger stuff, which basically defines, 1, whether or not there is a supercharger, 2, the multiplier on engine power for the supercharger, and the power cost of the supercharger. All right, next one we're going to talk about is turbine engine data. This one has to be present for both turboprops and jets, as well as helo turbines, and it's only got a little bit of data here to enter, not near as much as piston. The first one is fuel flow gain. This is which one is this actually? I often forget this one. This is a fuel flow gain constant, apparently. I don't know if it's a scalar so much, but you can use it to define fuel flow, I guess. I'm not really sure about that one. Inlet area, this is the square feet of the air inlet of the engine, basically. So we have 1 square foot worth of inlet air on this engine, which makes about sense. It sounds about right for a Caravan. Next is the max rated, or the rated into RPM. RPM of the second stage compressor rated value, 33,000 for the Caravan. And static thrust, 158 in pounds. Maximum rated static thrust at sea level. Now right under that we have turboprop. I believe the turbine engine data can actually have, it can have other stuff that's not present here. So let's go over that. Afterburner available. This is a simple flag, true or false if there's an afterburner. Now, that was true for older versions. For acceleration and beyond, that has changed. It's no longer afterburner available. Now, it's a numerical value between 0 and 6. 0 means there's no afterburner. 1 means there is an afterburner. And any number above 1 is the number of stages that the afterburner has. For example, the default Hornet has 6 afterburner stages. The next one is reverser available. This is whether or not the jet engine itself has a reverser. I don't think you need this for turboprops, actually, even though some of them might have a reverser, because that is done by the propeller on turboprops, not by the engine. But for some engines, like say the 737, they do have reverse thrust available. And this is simply, let's see, this is specifies a scalar on the calculated reverse thrust effects. A value of 0 will cause no reverse thrust to be available, and a value of 1 will cause the theoretical normal reverse thrust to be available. All other values will scale the normal calculated value accordingly. We also have thrust-specific fuel consumption. Jet thrust-specific fuel consumption, the ratio of fuel used in pounds per hour to thrust in pounds. This applies at all speeds. And you also have that repeated again for an afterburner. And then the last one you have is afterburner throttle threshold. This is the percent of the throttle range where the afterburner engages. On the default Hornet, that's 0.76 or 76%. So if you have 75% throttle set, the afterburner, your full engine power, but no afterburner. The second you cross into 76%, afterburner engages. Now, one thing, I don't know if I put it in here, but for jet engines, you also have to have jet engine data available, but there's only one thing that goes here, and it's a simple thrust scalar, which is the same as the scalars we talked about earlier. Now, turboprop engine, pretty similar. I don't think there's any extra info that's not present on here. Let's look. Turboprop engine. Nope, just 3 things go here. So power scalar, again, this is a scalar on power. 1.0 is normal. Maximum torque, which is the maximum torque available in foot-pounds. And you can also specify a power-specific fuel consumption, but most of the time this doesn't really happen for turboprops. I got it set to ignore this value anyway. Now, the last bit for engine data is propeller. Now, this is where we're going to be talking about things that are specific to the propeller. The propeller is required for aircraft that have a piston engine or a turboprop engine. I think helos use a different set. Yeah, they have an actual main rotor and second rotor entries, which I'm probably not going to go over because I really don't know that much about helicopters. Again, I'll link to some data where you can find this stuff. But basically, let's just go through what the propeller is. And again, like with the engines, most of this is pretty straightforward. Now, thrust scaler, again, a simple scalar on thrust for the propeller. Propeller type is a 0 is a constant speed and 1 is a fixed pitch. Propeller diameter, this is the diameter of the propeller, 8.8 feet on the Cessna Caravan. It's in feet. Propeller blades, how many blades does the propeller have? 3 in the case of the Caravan. Propeller moment of inertia, 19. Beta max, this is the blade pitch angle for a constant speed prop, the maximum blade pitch angle for a constant speed prop. So this would be the high RPM pitch of the propeller. In the case of the Caravan, it's 45 degrees. Now this is the minimum. Beta min is the minimum blade pitch for a constant speed prop. That does not include feathering, okay? Feathering is something else entirely. Beta min is 15.6 degrees on the Caravan. Minimum governed RPM, which is 25,520 on the Caravan, apparently. Prop time constant, I have no clue what that is. Let's check the SDK. Let's see, propeller. Let's see. Hold on, what was it I was reading? Mingo RPM prop TC. Prop TC, time constant for prop, minimum RPM controlled by the governor for a constant speed prop. There you go. Gear reduction ratio, the propeller gear reduction ratio, like I said, most of this is straightforward. The reduction ratio from engine output to RPM, it appears to be not really a scalar. All right, fixed pitch beta. This is the pitch angle for a fixed pitch prop, 0 in the case of the Caravan since it has constant speed. Low speed theory limit, the speed at which low speed theory becomes blended in. Prop sync available. Is there a prop synchronization available? There will also have to be a switch in the cockpit in order for this to work, or you can use the key command. Prop de-ice available. These are simple flags, 0 for no, 1 for yes. Prop feathering available. Prop auto feathering available. Minimum RPM for feather. Now, what is this exactly? Minimum RPM for feather. The minimum RPM at which the prop will feather if feathering is available. I think that plays into auto feathering. If you have auto feathering available, this is the speed at which the prop will actually feather. Beta feather, this is the feathering pitch angle in degrees. Power absorbed CF, this is the coefficient of friction for power absorbed by the propeller. Defeathering accumulators available. Are defeathering accumulators available? 0 for false, 1 for true. Prop reverser available. Is prop reverser available? True or false? Note we did not have reverse thrust available on the engine because we're in a turboprop aircraft. Now in turboprop aircraft, the prop will actually go through the feathered position and into a reverse position for reverse thrust. So turboprop reverse thrust is controlled by the propeller, not by the engine. That's why it's in this section. Minimum on ground beta. This is the minimum pitch angle on the ground. Minimum reverse beta. This is the minimum pitch angle in reverse. All right, for these last two, they're a bit special. I actually had to bring up another aircraft's CFG file to show you this stuff because it's very, very rare to see. These next two were added in FS9. They were added because of the Wright Flyer. So these next few entries allow you to specify the number of propellers you have, where they are located, and which engine drives them. If you remember correctly, in FS9, the Wright Flyer had a single engine that powered 2 propellers. So you can actually do that in FSX. You can have more propellers than you do engines. So firstly, let me specify that the implied default is 1 engine equals 1 propeller. So every engine will get 1 propeller by default. So if you're making a normal multi-engine airplane like the Beech Baron, you don't need to worry about any of this. There's no point in worrying about it. Just define where the engine is, like we talked about earlier, and then you won't have to worry about it because the sim will assume each engine has a prop. The second you define these, however, that changes. Secondly, I don't think you can do one of these then the other. I think you got to have both. And the reason being is because, well, you'll see as we go. So these first 2 sections here, these let you define the propeller number and where they are. So you can see here we have propeller.0, propeller.1. Usually when you see that dot, then a number, that means you can define any number of them. I don't know if there's any real limit, but here we have 2 propellers. The next is the engine map. Now this is a little bit different to the engine maps you might normally see. So let's go through it here. Prop 0 is located 6.9 feet behind, 6.2 feet to the left, and 3.1 feet above the engine that drives it. This is not relative to the datum. This is the one thing in the CFG file that I can think of that is not relative to the datum. It is relative to the engine that powers the prop, which you will specify down here. We'll talk about in a second. So remember that. Relative to its engine, not to the datum. The second propeller is pretty much the same, except it's only 4.2 feet right of the engine. So that's prop 0 and prop 1. The parameters you specify get carried over for each prop. Now, the engine map, this lets you specify which engines power which prop. So your normal engine map looks like this. This is a normal engine map. However, with the propeller engine map, that corresponds to the number of propellers, not the number of engines. So if I put 4 props up here, let's say I mapped out another 2, and then let's say I went crazy and put another 6, no, 2 more, so another 6. I would then have to increase this 2 more. So this is your number of props, not your number of engines. However, the number itself does indicate the engine. So for this case, this engine map, the first number is propeller 0. The second number is propeller 1. The third number is propeller 2. So on and so forth. All right, making sense. Hope I haven't lost you. Now, the number you put here is which engine drives that propeller. So if I put a 1 here, I am saying that propeller 0 is driven by engine 1. If I put a 2, propeller 0 is driven by engine 2. That also changes what engine it's going to be relative to. That means this will be relative to engine 2 wherever I put engine 2 in the engine data. So keep that in mind. Now, what would you use this for? Well, obviously with airplanes like the Wright Flyer, when you have a situation where 1 engine and 1 with multiple props, some vintage planes are like that. I can't think of too many modern planes. The only one that's coming to mind is the V-22 Osprey, which actually does have 2 engines, but the engines on the Osprey are connected, or at least the props are connected by a gearbox to the same drive system, so 1 engine can run both props on the Osprey. The reason being is because if you look at the Osprey, if an engine failed on the Osprey, you wouldn't be able to survive an engine failure in that aircraft. It needs both props to function in order to even fly. So that is how that works. So quick repeat: prop number, position relative to its engine, engine map, set the number of engine, the position of the number in the map is the prop, and the number itself is the engine. So the number can't be higher than 3 because you can only have 4 engines, but you can have however many positions that you have props. I hope it didn't confuse you too much. I hope that makes sense what I just said, but that's how that works. And that concludes engine data. Again, not going to go over helicopters because I don't know too much about them. Read the documentation I'm going to link down in the description. It will tell you a lot more. So that concludes engine data. Next, we're going to start getting into electrical and further systems data, and things are going to start getting a lot more fun because that's when we're going to start doing stuff that actually interact with one another and a functional aircraft starts to take form. So that's going to be fun. Stick around for that.